Okay, I'd like to introduce our next speaker, Beatriz, Jilete, and be telling us about sharing experiences from debris optical monitoring and attitude modeling. Thank you.
Thank you for the introduction. So good morning, everyone. I'm not going to introduce myself because I had the pleasure to do that yesterday, and you all know that my background is quite different to the majority of this audience. And I will just go into the content of my talk, which will give different perspective of the same problem, and sharing not only lessons learned, but I will reinforce, actually I will repeat 3 times along my speech, that we are looking forward to exploit as well the data that you are collecting in SatHub, because it's of interest on the space debris community. So as it was presented yesterday by Mike Peel, SatHub is divided in several components, so astronomical data repository, orbital solution portal, software tools, and so on. So that's why I divided my presentation touching base on those components, mainly astronomical data repository. So I will there give you a brief general view of the lessons learned that we have gathered conducting several observation campaigns and activities under the Space Safety Program in ESA in general, and particularly how it was materialized in something that I will explain further later on an operational Space Safety Expert Center. And the second part will be devoted to the software tools component, and we'll brief touch base only on 2 of the modules of the pipeline, so detecting restricting images and light curve of brightness simulations. So I'm not disclosing anything that is not already known, but data sharing needs to be done in a certain way if we want a consistent data set that serves as a source for further analysis. So there are many difficulties on combining data measurements from different sensors, and for example, we may get different precision level depending on the sensor type. So it's not the same getting information from surveillance sensors that you are going to have coarse estimation of the orbit positions than dedicated tracking sensors that you know already a priori orbit, and then you follow up the target. But also on the detector type. So you may have radars, laser stations, passive optical sensors, but with different detectors like CCD, CMOS, and all that includes influence in the precision. Also on the orbital regime. So in general, we devote radar sensors and laser tracking sensors for the LEO orbit. Then for the GEO ring, we devote passive optical sensors. And then we have high elliptical orbit or medium orbits that there we have to fuse the data. We have to do care as well on the reference frame and formats that all this data is delivered. So usually community from radar and laser stations, they prefer to use a topocentric reference frame, whereas TLEs are provided in TIME. So all those transformations needs to be taken into account, and also is going to introduce some outliers or errors. And then also the format. So for example, usually we make use of TDMs as CCSDS standard, but laser community relies on the full rate data format, CRD. And for example, for the light curve, there is still not existing an international or accepted standard, and each sensor or observatory is providing the light curves or is providing different kind of information in the light curves. We have to take into account as well the observation strategy that we are willing to follow. So it will depend on the objective. So for example, it's not going to be the same kind of observation strategy if we want to follow up a re-entry event or a collision conjunction event or fragmentation event. So fragmentation event in LEO, usually we make experiments with beam park radars. But we can think about as well on scanning the entire GEO ring following a leak-proof approach, or recently we have tested, and this is still presented before, I was involved in that campaign with a stare and chase. So basically you have a wide field of view passive optical sensor, you find an object, compute an initial orbit determination, update the TLE, and provide that updated information to a tracking laser station to further follow up and obtain more precise orbits. But also corrections assessments. I mean, it's not the same, we need to take into account epoch biases, astrometric accuracy, range biases, and those need to be applied in a consistent way. Otherwise, we cannot make sure that we are talking about the same. So all these topics that creates kind of a bit of a chaos was materialized somehow in the what is called a Space Safety Expert Center. So it's an operational center. It is the outcome of several activities that we have run in this space safety program, with the main objective to act as a hub between a heterogeneous network of sensors, mainly compiling laser stations and space debris laser stations, passive optics, and radar measurements, and SST data centers. And is basically taking into account all these application of corrections, calibration of the measurements, formatting, reference frame expression, etc. So right now it's hosted in the Astronomical Institute of the University of Bern, and they are under an activity of a space safety program. They are operating in it. They provide several services that have been developed around what is called the expert tools, which is basically in-house tools that they have developed in a specific centers of reference, like the ones that we have in IAUS and CODE and all these well-known establishments. So these kind of services that they provide, for example, is coordination of large amount of sensors. So in the upper plot there, for example, is a multi-target, multi-sensor coordination campaign. So we were willing really to observe same object from different sensors in order to have larger arcs and then predict better the position of the object. They provide as well services for what is called validation and qualification. And this is quite similar to what actually ILRS network is doing with the geodetic laser stations. So we want to make sure that the data that we are getting from the sensors is actually valid for the purposes of having an accurate maintenance of a catalog, right? Then we have to make sure that the data is consistent among them and we can combine. So for this validation and qualification, first the sensor that is willing to participate on this sign a service level agreement, perform a validation campaign that usually consists on 1-2 observation nights in order to understand which are the interfaces, formats, reference frames that they are making use, and a rough estimation of the quality of the data. Then we move to the qualification observation campaign that includes a more extensive observation campaign of several days in order to account different times in the night, but also in different days along a couple of months, to take into account all the effects that you may imagine, like seasonal and so on. And then there compute several KPIs, so latency on the provision of the data, astrometric accuracy that for passive optical sensors is estimated to be less than 1 arcsec in order to have derive accurate products out of it. For the laser, we compute the range biases that is estimated to be in the order of the centimeter in order to make sure that is valid data, and so on. And once the sensor performs of this validation qualification, these sensors becomes part of the pool of sensors that the expert center can query at the moment a certain observation campaign is of interest to be performed. It provides as well expertise, research and development of new algorithms, but also support on the standardization. And actually, they are now in coordination with the Interagency for the Space Debris Committee, so IADC, to develop a standard for light curves, so to make sure that every sensor that is providing light curves does in the same way and provides information because it's useful for after derivation of attitude. Another of the services is an attitude catalog. So they are running extensively observation campaigns to acquire light curves, and then they derive out of it the characteristic of the attitude, so they can assess whether the object is tumbling or not, and if it's tumbling, the rotation period. And then, just below you can see the 2 plots that actually for the computation of astronomical biases and range biases of 2 random sensors. I'm not going to disclose the names. And that, for example, I used to use a telescope that was shared with NEO community and myself. And of course, the data that we were getting from this sensor was referred to in a barycentric reference frame. When I were running the validation and qualification campaigns with the Expert Center, we realized the astrometric bias that we were getting were above 15 arcsecs, which is a lot, so it wouldn't be possible. So then we realized that we had to apply some corrections, like annual aberration, to actually translate the effect of being on the barycentric into the topocentric reference frame. And once we realized on that and correct on that, the astrometric accuracy of this sensor, it's in the order of the arc of secs. So these are the kind of services that Expert Center can offer. So of course, if you are willing or interested to exploit whether your sensor for this kind of information, you can ask in Slack the contact details of the university, and then I will provide you. So I changed completely the topic now, so I will focus on the software tools, and I will touch base only on two specific modules. So the light curve simulation, or brightness simulation, and satellite streaks detection in images. So the first of the tool is IOTA. So it was a software tool that was developed to assess and predict tumbling motion of a space debris object. It's highly modular and allows to perform short, so the simulation, like in the range of days, medium in the range of months, and long term in the range of years, propagation of the orbit and attitude of a spacecraft, taking into account the acting forces like atmospheric drag, solar pressure, third body perturbation, eddy current, torques, damping torques, etc. The processing module can generate ground-based synthetic measurements for observers and software validation. And it includes the generation of light curves, radar ranges, SLR ranges, radar cross-section, to enable direct comparison of what you are actually measuring with your real data. And we do believe that this module actually is of the interest of SatHub. It provides a visualization graphical user interface, and it is executed in command line. The inputs of this tool, so you have to provide the spacecraft model, then an initial attitude and orbital state, surface material properties, software-related settings like moments of inertia, radar absorption factor, magnetic tensor, damping dissipation model, surface reflectivity, and more. But also you can specify the observation campaign that you're willing to run, so in order to get light curves or SLR or radar measurements. And you have to provide as well your station, your ground station, so coordinate and main characteristics. So the output that you can get, for example, so in the center one is actually referring to how is the altitude of the MPSAT in this simulation was evolving. And in the other two, actually, is the light curve that you will have obtained if you had observed this MPSAT from Simmelbart Observatory in this case. And on the bottom figure is the SLR measurement that the range that you will get if you have observed it from GRASS sensor. It's available under a weak copy left license. The executable is distributable upon request, but only for ESA member states. The second tool I would like to mention is, but I won't go into the details because I do believe that is included in one of the SATCOM reports, is how to detect streaks in images. And this prototype was developed actually to find this streak and detect these streaks in a space-based sensor images.
2 minutes.
Thank you. I will manage. So originally was developed, I said that already, so it's coded in C++, inputs the image and user-defined parameters, you go through several modules and you get actually the strict information that you are willing to. It's not an open source, but code can be distributed under ESA common license via the URL that you can see in the slide. So to summary, it's going to be short, same message that I repeated since the beginning. We are willing really to get more in touch with you guys for actually create user-driven cases of data sets, of the data that you are compiling, because it's of our benefit as well. And then we can share knowledge on some software tools that we are developing, like the one that I have introduced, so IOTA and StrickDet. And that's it. So thank you very much for your attention. And any question I may take with pleasure.
Thank you very much.
You're welcome.
So we have time for a question or two.
It's not that technical. I wasn't expecting any question, I tell you.
Do we?
Oh.
Great. Super.
Yeah, thanks, Beatriz, for the excellent talk. Siegfried Eckel, UAUC and CPS. I'm extremely excited that you're willing to share and that willing to collaborate, with everybody on data sets. And I think defining a standard for light curves is probably something we could look into, even maybe at the hackathon, if you're interested.
Exactly, yeah. I was always thinking on hackathon, so that we can definitely talk about all this, yeah.
Thank you very much.
You're welcome.
Do we have another? All right, well, let's thank our speaker again.
Thank you.
Thank you.